All right, thank you, everybody. We have our second speaker for today, Melanie Jackson. Melanie received her doctorate from the University of Maryland Center for Environmental Science, Horn Point Laboratory in Cambridge, Maryland. Prior to her Ph.D. work, she got a master's degree at the same institution, studying algal blooms and nitrogen pollution. She's currently a Knauss Fellow she's the Congressional Affairs Fellow at NOAA Headquarters Office of Legislative and Intergovernmental Affairs. But today she's going to give us a presentation returning back to some of her roots in her presentation entitled The Benefits of Chesapeake Bay Oysters Beyond the Raw Bar.
Okay.
With that, welcome Dr. Melanie Jackson.
Thank you so much. Well, thank you everyone for coming out. I'm Melanie Jackson. I'll be talking about benefits of Chesapeake Bay oysters beyond the raw bar. This talk is a combination of a presentation I've given for the Maryland Shellfish Growers Network and Chesapeake Bay Foundation, a public talk for them, and, as well as my PhD dissertation work, which covered the characterization of the biogeochemistry associated with oysters on restoration and aquaculture. So let's start off with a spooky story. Let's see. It is. Should I point somewhere? There we go. Okay. So we know that human development has resulted in nitrogen runoff from fertilizer on our lawns, agricultural runoff, wastewater effluent. And when that nitrogen enters the water, it fuels algal blooms. And when those algal blooms sit at the surface of the water, they can shade submerged aquatic vegetation. And when those algal blooms die off, they suck up much of the oxygen.
Oh, I'm sorry.
They suck up much of the oxygen in.
Sorry, just give me 1 minute.
Yeah.
I got through. Okay.
There it is. Okay. So, when that nitrogen goes into the water, is the pointer working? Okay. When the nitrogen enters the water, it fuels algal blooms. And those algal blooms, when they die off, they suck up much of the oxygen in the water, resulting in potentially fish kills or dead zones. And so this has not just been seen in the Chesapeake Bay. This has been seen around the world. In fact, these red dots are pointing to areas where anthropogenic nutrient inputs have resulted in these declines in oxygen to less than 2 milligrams per liter. And so as a result, a number of best management practices have been applied to try and remove this nitrogen so that it's not entering our waters, such as cover crops, wetland restoration, wastewater treatment improvements. And so we have seen improvements over the years. There is less nitrogen entering the Chesapeake Bay. However, there's still too much fueling algal blooms. And so one of the potential mitigation strategies that's come up is more oysters. Oysters may be beneficial in that they're filtering out that algae that have nitrogen and storing that nitrogen in their tissues or meat. And when we shuck them, we're removing that nitrogen from the water completely. The other alternative is that oysters have good bacteria on their shells and tissues that turn that nitrogen pollution into air, removing it from the water and moving it so that it's not being taken up by algae. And so I will talk about that quite a bit more later. However, if we want more oysters, we have an issue. Overall, around the world, there's been a decline in oyster populations to less than 15% of historic populations. In particular, in the Maryland waters of the Chesapeake Bay, the most recent stock assessment by my Maryland DNR, Mike Wilberg from Chesapeake Biological Lab, have seen that just in the past 18 years, our wild oyster population is less than half than it was 18 years ago. And so there has been growing interest in oyster restoration efforts around the Chesapeake Bay, along the North Atlantic, in Europe. There are examples, Hong Kong, China, growing interest in using oysters for these reasons. At the same time, there's also been growing increase in the share of aquaculture production. And if you look at that blue bar in 2016, that's total aquaculture production. Mollusk aquaculture makes up a quarter of that total, whereas aquaculture from the oyster in the genus Chrysostria makes up about an eighth of that total bar. So it's small around the world. However, there has been a 32% increase in that Chrysostria production just since 2010. So that's quite a bit. But in Maryland, the past 5 years, there's been an increase in commercial aquaculture production from 1 million oysters to 22 million oysters just in the past 5 years. And so let's look at the numbers. Maryland's had a long history of commercial shellfish lease or private shellfish leases, and the proof is in the bushels. You can see they have a lot more aquaculture, whereas Maryland, there's quite a bit. We're still just scratching the surface. And then over the years, we could see that the growth in aquaculture, Virginia's really taking off on the East Coast. And so other than the fact that oysters are delicious to eat, they also provide great habitat for other organisms. In fact, some work on restoration site comparing restoration to bare mud and sediment has shown that restoration has 12 times as many organisms on that reef compared to barren mud. At the same time, aquaculture has been shown to have aquaculture equipment has been shown to have 32 times as many organisms around it compared to areas that don't have that gear. So it does provide good habitat for other organisms that we also like to eat, like crabs in the Chesapeake. But one of the main benefits that we think about with oysters is their filtration capacity. Myself and a number of others have called the oyster the vacuum cleaner of the Chesapeake, because they are filtering out that algae, either storing it in their meat or tissues, and whatever they can't are unable to consume, they spit out directly onto the mud, and some of that nitrogen is also being stored there. And so I'm sure some of you have seen videos of tanks with river water filled and showing that one oyster can filter up to 50 gallons of water in a day. But I wouldn't be a good scientist if I didn't show you the nitrogen storage and some data. So my advisor, he has been leading this panel on the oyster best management practice. And they've seen that as the shell height of an oyster increases, the nitrogen storage in those tissues and the shell increases as well. But the ecosystem service that I've been most interested in and was the main part of my dissertation work was looking at denitrification. Has anyone ever taken probiotics in this room? Yeah, so if you're putting in probiotics, you are putting good bacteria into your gut to try and remove all that bad stuff that you ate the day before. Whereas oysters have good bacteria on their shells and in their tissues that are taking that nitrogen runoff and turning it in the form of nitrate and turning it into dinitrogen gas, or essentially air. And so that nitrogen is being removed from the water and going into the air. And so that was what I've focused on. And this is, this gas is pretty elusive. It's not easy to measure. A lot of people have tried to measure nitrogen removal a number of different ways. Some people have measured nitrogen removal using 50-foot long tunnels. Our lab has used these in situ acclimation, ex situ incubation techniques, in that these trays are acclimated out in the field for about a month, and then we bring them into the laboratory to pull the measurements from. Other people have measured this out in the field in situ chambers. There's been a lot of different methods used, whereas other techniques have involved sediment cores adjacent to the reef. So they're not necessarily looking at the oysters, but the biodeposits around them. And then finally, the last version is measuring the oysters alone. And so this made me wonder, what role do these oysters play? Should we be including them in our measurements? Is it just the sediments that are helping do this process of nitrogen removal, or is it the oysters themselves? And so let's see. I will walk you through three of the more interesting parts of my dissertation, looking at restoration and what role those oysters play in that nitrogen removal. So we worked with Lisa Kellogg from VIMS, and her dive team helped put together these trays that you see. She's holding, the scuba diver's holding a tray. They would fill those trays with sediment and oysters and put them out onto a restoration site flush with the sediment. And they would let them acclimate out there for about a month. After a month's time, they'd go back out to those same trays and cap them off and seal them up, and they would bring them to the laboratory all the way on the right, where we would seal them up, put them in temperature-controlled water chambers, and have the change the lighting for the acclimated lighting, and we would seal them up and pull water samples over time to measure that nitrogen gas production. And we saw that the oysters were producing that nitrogen gas from the whole entire acclimated reef. Now, following this experiment where we looked at the acclimated reef nitrogen production, we pulled the oyster clumps by themselves off of that acclimated reef to incubate them by themselves to see what portion of the total they were producing. Sorry, this is slow. Okay, so here was our study site. We were on the Choptank River, specifically in the Harris Creek restoration site. So those trays were acclimated out in Harris Creek, and they were brought into the lab after a month. And then, so what we did was, once again, we incubated those whole entire trays with the sediment and the oysters, and then we incubated the oysters by themselves. And so what did we see? Okay, so on the x-axis, on the left-hand side, we have the total oxygen demand from that entire tray. On the y-axis, we have the oysters by themselves. And what we see is, as the total oxygen demand increased for the total tray, the oysters by themselves tended to overestimate the total oxygen demand, which this makes sense. We were pulling those oyster clumps off and incubating them by themselves, exposing mud that had been under other sediment, and we were oxidizing it. So we were expecting the oxygen to be a little off when we incubated those oysters by themselves. And dissolved in organic carbon on the right-hand side is just another proxy for that respiration that's happening. Okay, and then when we looked at the nitrogen removal, on the left-hand side, what we saw was that on the y-axis, those oysters alone tended to underestimate that total nitrogen removal. So we can use them as a base number for that total nitrogen removal because they were not higher than that. And the interesting part on the right-hand side was that we saw that the nitrogen removal increases as the oyster biomass also increases. So as you have more oysters, you're likely to have more of that nitrogen removal happening. So now that we understand that the oysters have an impact on that nitrogen removal, let's see how oyster aquaculture harvesting impacts that nitrogen removal. So what we did was we took sediment cores from 3 different sites on an aquaculture lease, from a site that had not been planted with oysters, a site that was planted with oysters and just harvested that morning, and a site that was planted with oysters and had not been harvested yet. And this was in the Nanticoke River on an on-bottom oyster aquaculture lease. And so we went to these 3 different sites during May, July, and September. And that sediment core on the slide is from a site that was just harvested that morning. And if you look closely, you could see anemones, tons of polychaetes. So even though it was just harvested, there are tons of organisms that are still living in there, which was really incredible. And so we brought those sediment cores into the lab on the right-hand side under ambient temperature and light conditions and pulled the water samples from all these different cores. And just to give you a little bit more background, we saw that the nitrate at the site, NOx, was much higher in the spring and early summer and declined. And so this may feed into how much nitrogen is being removed. And in fact, that was the point. In May, we have the white bars, the site that was not harvested, we just incubated sediment. The site that was not harvested but planted is the light blue, and the dark blue is a site that was harvested that morning. And so those sediment cores are showing that following the harvesting, the nitrogen removal was much higher after that oyster aquaculture harvest, which is really interesting. But it was only during the month of May, which is when we had those higher nitrate concentrations. So you need nitrogen in the water to remove it. Okay, so now that we know that the aquaculture harvesting does play a role in that nitrogen removal, what about size? Does that matter? And so what we did was pulled oysters from that same aquaculture lease and incubated small, medium, and large size classes of oysters in those same incubation trays by themselves to see, okay, we know that a certain size oyster has this much nitrogen in its tissues, but can we use that oyster size to determine how much nitrogen they're removing also? And let's take a look. So these are some incubation chambers that I built specifically for this experiment so that they could fit the oysters. And there we are with 16 of those chambers to hold the different sized oysters. And so the small ones, we had 4 different batches of small ones, 4 mediums, and 4 larges, and some just with shell. And this involved lots of shucking of oysters, drying them. This video is showing polychaete worms that were attached to the shell. You'd be surprised that depending on how oysters are grown, I found as many as 100 polychaete worms that I would extract from the shell to see if they were playing a role in this nitrogen removal too, because they're also feeding, filtering, spitting out algae as well. And so what we saw was, just for reference, as the oyster size on the x-axis increased, the tissue biomass also increased. This makes sense. The bigger the oyster, the more its meat will weigh. But the interesting part was that the oysters I collected in May had a much higher biomass than the ones in July and September. And this kind of makes sense in that in the Chesapeake Bay, the spawning period for oysters increases from the spring to the late summer, and the peak spawning is in July. So these oysters were likely lighter due to a recent spawn because these were diploid oysters. Sorry for the delay. Okay, so what we saw was as the oyster tissue biomass increased, the oxygen demand for the oysters also increased, and this makes sense. And the oyster respiration also changed depending on the temperature. So you could see the y-axes are much higher in September when the temperature was warmer than in the early spring. But what we really want to see is this nitrogen removal. And it was pretty interesting in that as the oyster biomass increased, the nitrogen removal increased with size, but only in May and September. This may have something to do with that spawning or some of the polychaete worms, but it's unclear at this time. And so we do know, though, that oysters contribute to the respiration in the water. They're helping remove that nitrogen, and they remove a considerable amount compared to sediments, and as well as the aquaculture activities, the nitrate concentrations, and the temperatures. All these environmental characteristics really impact how much nitrogen is being removed. And so we still have a lot to learn before we apply this as a best management practice. But we do know that once major sources of nitrogen are addressed, that oyster aquaculture for coastal nutrient remediation would have an added economic and environmental benefit. And the environmental and ecological value is a function of the cost of these alternative nitrogen removal pathways. And how we measure this also has a huge impact on how much nitrogen we find out they are removing. And with that, I'd like to thank my sources of funding and fellowships, as well as, this took a large community to pull all this work together. So I was not alone, especially the Horn Point Oyster Hatchery. So, and with that, I'll take any questions.
Anyone have questions for Melanie here?
Okay. Spooky stuff.
I'll give you a minute to think. So.
Oh yeah. Oh yeah.
So thanks for the great presentation. At the end, you kind of posited the idea of future best management practices with the effects of anthropogenic, or to kind of combat anthropogenic nitrification. Could you maybe, I know that kind of there's a lot of science still to settle and more experiments to do, but could you provide some examples of what that might look like of best management practices? Is it kind of integrating into some restoration projects, or I know oysters often are also, oyster reefs are also associated with kind of like gray infrastructure or protecting coastlines. Could you maybe expand or hypothesize on some of this?
So one of the easiest best management practices in terms of the oyster that would be easiest to apply would be the meat itself. There's been so much data on the amount of nitrogen that's in the tissues that there's been a lot of research quantifying that. There's been a lot less research quantifying that denitrification portion that I talked about. But in terms of the meat or the nitrogen in the tissues, it's very easy for aquaculture to say, okay, this farmer put in this many oysters, and in the end, they were approximately this size. And if we're going to take them out of the water and shuck them and eat them, we know that that's how much nitrogen is being removed from that meat. And so that's one of the easier ways, more applicable best management practices that could potentially be used. It gets a lot more complicated with restoration in that, we're putting out those oysters and then it's a sanctuary and they're not going to be touched. The denitrification component of it becomes a little bit more interesting in that as these reefs get older and if the oysters are getting larger and larger, then we may know that that denitrification is removing much more of that nitrogen, whereas we're not removing those oysters to eat. Yeah.
So thanks for that. That was a wonderful presentation. I always love oysters, so great to learn more. One question I had was in terms of the sites that you were selecting. So in terms of the site selection for the aquaculture, the restoration, how did you all go about determining that? Was it based on nitrogen levels in the water, or was there some other factors, which I understand in terms of ease of access and things like that, but I was just curious.
No, in reality, it was a moment of opportunity. The restoration site, my advisor had some funding from NOAA and NSF on that. We did this Oyster Futures project with Elizabeth North and Mike Wilberg, bringing in oyster watermen to talk about oyster management practices. And we even brought the nitrogen removal component in there and did some folks did an economic analysis on that. So that was a interdisciplinary project on that. And so, you know, just because that project was there, we chose that site. And that was one of the larger oyster restoration sites in the Chesapeake at that time. And so, whereas the aquaculture, finding a waterman that was open to me stealing a ton of his oysters and asking me to show him, or me asking him to say, okay, can you bring me to the site you went to this morning and, you know, that you just harvested from, getting that was number one. But there are a ton of different types of aquaculture too, though. So like this was just on bottom, but, you know, there's lots of different types of off bottom aquaculture we could have sampled from. And there's been some other work about that, at least in the Northeast, related to that sort of work. So yeah, finding someone willing to let us steal their oysters.
Hey, does anyone else in the room have a question for Melanie right now? Okay, so yes.
So I know I probably could have read it from your graph there, but you had the relationship between oyster size and denitrification. So did that increase per unit mass as they got bigger, or was it just bigger ones?
Per unit mass.
Okay,
so that was.
Wow. So they get better out of the bigger they are.
Yeah.
Cool.
So let's check if we have some online questions. Okay, so we don't have any online questions right now, so we'll end it here for today. But thank you very much, Melanie.
Thank you.